Max Kasy. He's a professor of economics at the University of Oxford. Received his PhD at UC Berkeley and joined Oxford after appointments at UCLA and Harvard University. His research interests focus on social foundations for statistics and machine learning, going beyond traditional single-agent theory. He also works on economic inequality, job guarantee programs, and basic income. He teaches a course on foundations of machine learning at the economics department at Oxford. In fall 2025, his book, The Means of Prediction, How AI Really Works and Who Benefits, was published by the University of Cambridge Press. So Max, we look forward to hearing from you.
Thank you. Right, good morning everyone. Thanks for coming out despite the rain. So I'm going to try and continue in the spirit of the talks we saw yesterday morning. Gonna discuss some kind of more big picture thoughts or arguments around like the intersection of machine learning, causal inference, and economics. And I guess the main idea is to think about possible new research agendas or things that we could be working on in addition to the ones that have received a lot of attention already. And so, I mean, there's some intersections I think that a lot of people, including a lot of people in the room, like Whitney and others, have spent a lot of time on, which is thinking about machine learning as a way of producing first-stage estimators in semi-parametric estimation problems, and more specifically in settings like double robust estimation of treatment effects under assumptions like conditional exogeneity of treatment. And I think that's interesting and useful, and it's very useful to have kind of a plug-and-play approach where you can kind of take estimators like double robust estimators and plug in first-stage estimators coming from new machine learning procedures, especially for kind of non-traditional data formats or kind of very high-dimensional data. But what I'm going to try and argue in this talk is that there's also a lot more out there that we could be working on at this intersection between causal inference, machine learning, and economics. And what I'm going to do is I'm going to make six high-level arguments, where many of those are kind of based on old ideas, old points, and then I'm going to elaborate these arguments again in some more detail and some more formality in the context of binary choice, which is one of the classic workhorse models for econometrics and economics. All right, so argument number one, something you would often hear is machine learning is purely correlational. It's just about predictive patterns. It's about estimating things like conditional expectation functions or conditional probability distributions. And so that's kind of conceptually distinct from causality, and so therefore we need to introduce causality as a new concept into machine learning. And I think that's kind of half true. That applies to supervised learning, which is a lot of machine learning. But it's not true for kind of the other half of machine learning, which are things like reinforcement learning and multi-armed bandits. And so what I mean by reinforcement learning here is, the term is used differently by different people, but it's kind of in the general sense of having algorithms that make decisions. Those decisions are implemented in the world or some environment, and then the algorithm observes the consequences of these decisions. Right? So there's kind of a different information flow here. Like in supervised learning, the information flow is one directional. The data are just being produced and they're coming in, and then the algorithm analyzes them. Whereas in reinforcement learning, in this sense, there's kind of a two-way flow. Information comes into the algorithm, it's processed in some way, then the algorithm makes decisions, acts in the world or in the environment in some way, and that produces new information. Right? And every time that happens, that kind of immediately leads us to causal inference in some sense. Now, that's true, and in some sense it's a very well-established and well-understood branch of machine learning, but at the same time, kind of the causal inference part of it usually remains implicit. Right? So when you read textbooks on reinforcement learning or bandits or related subfields, typically they don't use the language of causal inference, even though what they're doing is exactly causal inference. And I think there's a reason for that, and the reason is that the causality that's of interest there is always the causal effect of actions chosen by the algorithm on some observed rewards or loss functions, depending on how you choose the sign. right? And because the actions are always chosen by the algorithm, they're by construction exogenous, they only depend on information that the algorithm has. And so because of that, in some sense, causal inference is trivial, right? Because you're interested in the causal effect of the actions that you choose, but those actions are by definition exogenous or by construction. And so you don't have to deal with the things that the econometricians spend their time with, like I don't know, instrumental variables or regression discontinuities, or you name it, all these different approaches to try and find variation for causal inference. And I think that there's kind of, again, a more general reason for that, which is if you look at how we define causality, right, there's different traditions and notations in different subfields of statistics. Like econometrics traditionally talks about structural functions, biostatistics, and more recent applied econometrics talks about potential outcomes. Computer science with Judea Pearl and others talks about the do calculus. And there's been kind of a lot of heated debate over the years, like which of these is the better notation. For my purpose, they are all kind of the same thing. And in particular, they're all based on this idea of an exogenous intervention, right? The way causality is defined in all these different formalisms is always there's something coming from outside the system, often based on the decision of a human or an algorithm, or maybe based on some kind of natural experiment. And that allows us to identify causality or even define causality, that there's something coming from outside. But that's a kind of exactly the same thing that we also talk about when we talk about decision making, right? And so again, like decision theory and decision making is often discussed separately from causal inference and experimental design, but there's a lot of overlap again between the two, that they're both based on this idea of intervening and then observing the consequences of the intervention. And in reinforcement learning and bandits, that's kind of baked in, that you're simultaneously intervening because you care about the consequences of your action, but you also use that to learn about these consequences and about the causal effects. Now, kind of the next three arguments are kind of more about the economics of this in a way that complicates this perspective a little bit, and in some sense makes it harder, in some sense makes it easier to do causal inference. Where kind of, the next point here is the type of outcomes we care about as economists, and especially if you think about like policy, like public policy for some notion of social welfare, then those outcomes are not directly observable for fundamental reasons. Right? So the way economists typically define social welfare is as some kind of weighted sum of utilities of different people, and we don't observe utilities. Utilities are indirectly defined based on what people would choose, but we observe our actions, and so we can infer utilities from actions indirectly, but we never observe the utilities themselves. And kind of so simplest classical example, which you might have seen in a variety of intro econ courses, is we can infer consumer surplus by integrating demand functions, or similarly for labor supply functions and other settings, right? And so we can use observation to infer our objective. We don't observe the objective directly, but when we think back now to settings like bandits and reinforcement learning, that changes the exploration-exploitation problems you face in these settings, because you need to experiment in a different way. In like a standard multi-armed bandit, right? So bandits are settings where you choose actions, you observe the rewards, and you kind of face a tension between, on the one hand, choosing actions that allow you to learn a lot, to make better choices in the future, versus making choices that have good reward now. That's the exploration-exploitation trade-off. And that changes if your goal is to maximize some notion of social welfare, because in that case, you need to also explore away from potentially optimal policies, because you care about these integrals rather than just about, say, the value of the demand function at the point. Right? And so that's a solvable problem, but it changes how we should think about adaptive experimentation or reinforcement learning if we care about these types of welfare objectives. Next, and so here I'm going to contradict slightly a point that was made yesterday morning. What's often described as the fundamental problem of causal inference is when you choose an action, so you assign a treatment, you observe the potential outcome corresponding to the treatment, but you never observe the counterfactual potential outcome. And so because of that, you never get individual level treatment effects. Right? So the counterfactuals always remain missing data in a world with heterogeneity, in the social sciences, life sciences, where there's a lot going on that we never observe. We can only ever hope to get something like average causal effects, but never the individual level causal effects. And so that's true in many settings, but there's also many settings in economics, especially where it's not true, I think, which in a way is like a very old insight, but took me a while to appreciate at least. There's a lot of settings where we can use ideas from mechanism design, and I'll explain later in detail what I mean by that, to elicit preferences and to recover response functions. So the example I'll talk about will be, say, demand functions, right? If you think in terms of these potential outcomes, you can randomly assign prices and then observe how people respond, or tax rates or other things. And if that's what you do, then this is true. But alternatively, you can design a mechanism where you ask people how much they are willing to pay for something. And if you do that in the right way, the best thing for them is to respond truthfully. And if you know how much everybody's willing to pay, you can kind of get the entire demand function. So kind of in one shot, you get all their counterfactual decisions. Right? And that makes, in some sense, causal inference a lot easier. So that goes in the opposite direction of this point. This is a reason why it's harder to do counterfactual inference on welfare. But if you're able to use mechanisms like this, it's a lot easier to do counterfactual inference, because for every individual in your data, you don't get just one potential outcome, you get all their counterfactual responses to say, like prices, taxes, and other interventions like that. And lastly, this argument here is about kind of getting your willingness to pay or preferences over things that you make choices over, and that's very important. But then there's also you're also impacted by your own choices, often impacted by the choices of others. And so, for instance, pollution would be one classic example. Data sharing is another one with data externalities. So that's what economists call externalities, is that our actions impact others in a way that they have no say over. And that makes, again, causal inference or identification difficult, because my behavior only ever tells anything about my preferences over my own actions, but not over the actions of others. But turns out, if you tweak these mechanisms that I will talk about here a little, there are things you can do in order to also elicit preferences over the behavior of others. And so this is something I'm currently working on, trying to figure out ways of incorporating that into adaptive decision making, which is important if you think about settings like congestion pricing or say the governance of data collection, where we care about the impact of people's actions on other people, and we want to get to optimal levels, say, of traffic or other things. All right. So, by the way, the second half of this is going to get kind of economy, so please interrupt me anytime if you have questions. But basically what I'm going to do for the rest of the talk is, again, going through these 6 arguments more slowly and more formally, to elaborate them and kind of spell out how that works in the context of binary choice. So what's binary choice? Again, kind of a canonical workhorse example for economists. The idea is there's individuals I. These individuals are exposed to some price. Just for convenience, I normalize that to be in 0 to 1. So I'm going to denote the price here, xi. And then every individual has their own willingness to pay for something, right? So you could think about this, say if it's congestion pricing, it's your willingness to pay for driving your car or something like that. Or it could be your reservation wage, the minimum wage at which you're willing to accept a job, or all kinds of other things like that. And so if individuals are exposed to a price xi and their underlying willingness to pay, their preferences are vi, then they are going to make a binary choice, yi 0, 1, drive your car or not drive your car, accept the job or don't accept the job. And then the observable choice is yi, which is equal to 1 if the price is less than the willingness to pay, and it's 0 otherwise. Right, so that's kind of a canonical binary choice model. And so with that setup, we can talk about potential outcomes. potential outcomes is just a choice that individual I would make if they're exposed to the price little x here. And then we might also have other covariates. They're just kind of exogenous here for my purposes, but they might be correlated or statistically dependent with this underlying willingness to pay. Okay? So this is the setup I'm going to talk about for the rest of the talk. All right. Now, what can we do in this setup? So the first thing we can do is just do our standard causal inference, right? We can think about settings where we exogenously or randomly assign prices to people, statistically independently of people's willingness to pay, right? That's what it means to be exogenous. And then we can just identify demand functions by basically regressing choices on prices, right? So we can identify the average potential outcome or average structural function, the expectation of y of little x, right? So here, this is a fixed exogenous x, and that's just given the statistical independence of prices and willingness to pay, the same thing as the conditional expectation of choices given prices. Right, so if you have exogenous assignment of prices, you identify structural functions or treatment effects or average potential outcomes just by a simple regression. Now, in this setting, what you often hear people saying is canonical machine learning is not about causality, right? It's about predictions, it's about conditional expectation functions, conditional probability distributions. It can be used to estimate things like, for instance, run a regression, for instance, of choices on prices and covariates, and then you get this function gxw, but that's not a causal object, it's just a purely predictive or correlational object. Or similarly, you might estimate the conditional distribution of prices given covariates, and again, that's kind of a purely correlational object. And that's conceptually distinct from causality. Correlation is not causation, because causation is about objects like average treatment effects, for instance, for going from a price x0 to a price x1, right? And those are not the same. Now, how do you bring them together? And something that we've seen quite a bit of work on, and I guess half the speakers today are on this paper here.
Thomas?
Oh, sorry.
I just had a question.
Yeah.
So in your setup, the 2 slides back, so just so I understand, and maybe you're going to get into this, but I mean, if I know that you're being offered a lower price, even if the price that I'm offered is what I'm willing to pay, I might feel like, no, I'm going to wait until I get randomly assigned a lower price than you were being paid.
Yeah, so here I guess the assumption is you can't do that. It's not like it's happening over time and you're just waiting for one unified price. I decide your price, me as the experimenter or decision maker, and you have to live with that.
But I mean, practically, information flows. So if you're randomly assigning prices, are you assuming that there's no communication? I'm unaware of prices other people being offered.
Not in this setting. In the real world, of course, this happens many times, but and there's kind of secondary markets and all kinds of things. Here I'm trying to talk about the most stylized, simple economic setting possible, which is you make one binary choice, you face a price for the choice, and that's it, right? And yeah, and we can talk about how many settings there are where this applies, but I'm trying to make some conceptual points in this setting. Which, I mean, I'll get to online pricing in a little bit. I think it's not that unrealistic in many settings where different people face different prices online. Say you buy a plane ticket online or something like that, right? It's hard to do like a secondary market on plane tickets because it's in your name. So it depends,
But there are websites that track it, for example.
For sure, yeah. Again, I'm not saying this is the realistic description of all the real world. I'm saying this is like a canonical, minimal example that allows me to make a lot of these conceptual points. All right, so now if you take this perspective, right, machine learning is about estimating correlational or predictive objects of this sort. Causality is about average treatment effects or similar objects of this sort. How do we bring them together? Well, one natural way to do so is that there are various settings where it's sensible to use like a 2-stage or multi-stage estimation procedure, where in the first stage you need high-dimensional objects like regression functions or prediction functions of this form, right? Like the this regression of, say, choices on prices and covariates, or the regression or prediction of prices given covariates. And so we can use machine learning as a first stage to generate first stage estimators of these objects, and then plug them into second stage estimators of the causal objects that we care about. And that works under some assumptions, like for instance conditional exogeneity, if prices are random or independent of willingness to pay conditional covariates. Right? So you could think about simple plug-in estimators where you just take your regression function g of xw and average it out over w's. Or you could use slightly more involved procedures like this type of double robust influence functions. And again, plug in first stage machine learning estimators. And under some conditions, this is going to yield good procedures that are in some sense robust to whatever is happening in these first stage estimators. And machine learning might allow you to deal kind of with non-standard data formats of very high dimensional first stage problems and so on. All right. Now that's all in kind of this setting where the data are just given to us, right? And then the algorithm or estimation procedure uses the data and produces estimators based on that. But there's this whole part of machine learning, and I guess statistics more broadly, where data are not just given to us. Instead, we do things like survey design, experimental design, and the machine learning counterpart is reinforcement learning bandits and so on, where the information flows in two directions. There's information flowing into the algorithm, which is being processed in some way, and then the algorithm acts upon the world in some way and observes the consequences of these actions. And so, I mean, that's basically what leads to experimentation. Now, the way machine learning folks would typically think about that is that you kind of simultaneously care about learning and about the outcomes that you're doing. Right? So social scientists or life scientists traditionally kind of separate the two a bit more. You run experiments that are just for causal inference, and then separately you choose policies, say in a clinical setting or something like that, that are implemented in a large scale. Whereas in the ML settings, it's typically kind of folded into one, and that gives you settings like bandits or reinforcement learning. And so, right, typically it would happen iteratively. Every time period, say, you get a new unit of observation coming in, a new individual in my setting. We choose an action like the price X, and then you observe the reward for the chosen action, and then you iterate. And so this kind of folds the decision problem and the experimentation problem into one. Yeah, and so your actions are also about generating the data that you get. So in the binary choice problem, one example that has received a fair amount of attention is adaptive pricing, right? It's kind of a lot of what the big tech companies might be doing is choosing prices to maximize the profits. And so as a simple version here, like assuming, say, that their production cost is 0, then their profits are just equal to the price they charge xi times the binary action of the customer that they face. So it's yi times xi is the profits, ri, the reward function. Correspondingly, they have potential profits. And kind of in a slightly stylized manner, a lot of what might happen online is something like they observe some covariates, right? Whatever data they collected about you with their cookies and user profiles and whatnot. Then they choose the price that you face, and then they observe the corresponding reward function, which is kind of one-to-one with the binary choice here. And the goal is to maximize the sum of rewards over time. So this is, in some sense, a special case of the bandit problem, or a contextual bandit problem, given the covariates, where the experimentation is used to learn the mapping from prices and covariates to expected profits as a function of prices, conditional and covariates. Right, so this is a causal object, kind of like a conditional average treatment effect, conditional average potential outcome. And then they want to use this knowledge to generate high profits. And kind of the tension in these algorithms is between exploration and exploitation, choosing actions that generate new information that's useful for the future, versus choosing actions that yield high profits now. But one thing to note here, and it will be important in a minute, is the type of exploration you need to do here is really only for potentially optimal actions, optimal price levels. Right? If I know that, say, if I set the price to the maximum of 1 here, then nobody is going to buy anything. That's not a useful price to ever consider. There's no point to ever experiment there. And instead, I want to focus my attention on prices that are potentially optimal, because those are generating information that might be useful for my future actions. Now, again, this is a causal inference setting. It's almost never discussed as causal inference, or not explicitly. And again, there's kind of, I think, a reason here. And just to spell out something we've already talked a bit about yesterday morning, how we think about causality here. That is a little bit different from how, say, at least a stylized version of physics would think about it, where in the stylized version of physics, what we do is we prepare a system, right, an experimental setting, ideally with perfect control. We control everything that matters for the system at hand. And then we observe the outcome, and every time we prepare the system in the same way, the same thing should happen. And then if we prepare it in a different way, observe different outcomes, and then that's kind of the causal effect. And that gets at something like an individual level causal effect here, because at least in this idealized form, we've eliminated all heterogeneity. That's never possible in the life sciences and social sciences. Unobserved heterogeneity is pervasive, and so a controlled preparation is impossible. But in a way, that's this kind of recognition of unobserved heterogeneity is I think, a lot of what has driven applied causal inference, applied econometrics over the last few decades. We're talking about things like local average treatment effects. That's something that becomes visible once you're kind of serious about recognizing this heterogeneity, and which basically means that causal effects vary across units, and therefore you don't get these individual level causal effects. And so with this effect heterogeneity, then it matters in some sense for whom you get variation with your...
I'm a little bit confused about the distinction you're drawing between the top and the bottom, because, you know, quantum experimentalists do the above setting all the time, and quantum is inherently stochastic. But you talk about counterfactual outcomes nevertheless in the top, not average counterfactual outcomes. Is the difference like where the uncertainty lives that you're averaging over?
I mean, again, I don't want to push this too hard to saying that this is really what happens in physics, especially in like whether it's thermodynamic systems or quantum systems and so on. I mean, in some cases it averages out, right? But absolutely, there is uncontrollable heterogeneity, even if in classical settings, right? We never have perfect control. But just as a kind of a conceptual ideal, I guess. I think there's a different order of magnitude of heterogeneity that we cannot control in the life sciences. You might well argue that this matters in the physics settings too. The point is that we do, in the life and social sciences, we certainly do have this heterogeneity, which I guess is part of the point of what we talked about yesterday. Yeah. I mean, I don't know, not to get too philosophical here about physics, but I guess in quantum mechanics, I mean, at the level of the underlying state, it is deterministic, right? It's at the measurement stage that somehow stochasticity comes in.
I think people will strongly disagree with you.
Fair enough. Let's not get into the discussion, but you have like a Hamiltonian that gives you the evolution of wave equations that's deterministic. But anyway, yeah. All right, but what is kind of baked into this here, which is incidentally different from what my understanding is people in philosophy or metaphysics talk about as causality, is that the notion of causality is
On your point about repeated interventions in social systems, which I guess is quite crucial for the other stuff. I guess that only works if there's that you can assume some sort of independences in the system, right? So, like,
or the exogeneity, I guess. Yeah, that's the general way of putting it.
but like, we can often not have repeated interventions as well, right? So, how would you say how important that is?
I think it's quite important, right? Like, I think that's a big difference in economics, say, between like micro and macro settings. Like in applied microeconomics, typically you think about interventions at the level of individuals or maybe at the level of firms or villages or things like that, where you have a lot of comparable observations. If you care about the macroeconomy, there's only one Great Britain of the, 2026. And so there isn't really a counterfactual observation often for what you care about. So that makes it a lot harder to think about causality there.
But even in the micro world, your assumption is some level of independence across those units, right? When you're saying you can't do these repeated things.
You mean causal independence or statistical independence?
Causal.
Yeah, so no spillovers.
Right.
Yeah, absolutely, yeah. Which might or might not be true across different settings, right? But yeah, to talk about something like an average treatment effect or maybe sample average treatment effect or things like that, we have to talk about multiple units that we're averaging over and for whom we can identify this average, as opposed to the individual level treatment effect. But again, I'm going to kind of contradict this in a few minutes by talking about mechanism design and talking about how we actually can get at the individual level treatment effects in some settings. But again, what I want to emphasize here is that really what this notion does, which is what philosophers call an interventionist notion of causality. It's really about this idea of you have a system, whether it's the system of physical experiment or the system of I don't know what's happening with an individual or a firm or something, and there's something is coming from outside the system. That's the exogenous variation. And that's kind of what allows us to define causality. Causality is kind of the answer to what happens with exogenous variation, right? Which is different again from how people in philosophy or metaphysics talk about causality often, which is more about relying on things being contiguous in time and space in a way and being connected to some chain of direct relationship, and where there is no outside in some sense, right? To talk about this, you have to talk about an outside of the system because there's something has to be exogenous, generated outside. And where it's generated often, right, which is not necessarily but typically the case, it's generated by an intentional actor, whether it's a human experimentalist or an algorithm that's choosing actions. And so that's how this notion of causality again is intimately tied to decision making, I think, where again decision making is about somehow given whatever information you have, and then you make a choice with the goal of maximizing some reward or some utility or minimizing some loss, which is similarly about this exogenous intervention. And so in machine learning, in fields like reinforcement learning and bandits and so on, this is kind of folded in. It's simultaneously about decision-making and experimentation in a way. Yeah, that kind of equates the two.
I just have a little bit of trouble trying to understand a reinforcement learning algorithm as exogenous, because its actions are an algorithmic function of previous observations.
It's exogenous conditional on the information that the algorithm has. Right? Because, I mean, it's almost tautological because the algorithm chooses the action.
I don't know what choice means here, because the algorithm is running a deterministic procedure to decide what to do next. So its action is a deterministic function of it.
Depends. I mean, some algorithms are randomized, and often it is what you might want to do. But either way, even without randomization, you can have a deterministic algorithm. Right, so the typical examples are things like algorithms like AlphaGo or AlphaZero for gameplay, or like you run a clinical trial where you're kind of choosing for every patient what treatment they get. Might be online price setting or ad targeting, the selection of feeds on social media. Those are typical like reinforcement learning or bandit settings, where algorithms choose based on the history of information they have, based on the information they have on the unit under consideration, they choose an action. And when they do that, then they can immediately use that to do causal inference because the action is, again, only depends on information that the algorithm has, and maybe a randomization device.
So is this basically a statement about conditional independence between the past on which it's basing its decision versus the thing it's going to...
It's independence of the action and unobserved heterogeneity, conditional on the past and whatever the information the algorithm has. But it's just... it's really having the type of conditional independence you need for this kind of canonical treatment effect estimator, right? That holds kind of by construction in these settings. So you don't really have to talk about in any more sophisticated way about causal identification in the sense of like thinking about instruments or regression discontinuities or difference designs or any of those things.
And just as a comment, I think for some people, thinks that it's a little strange to have something that's exogenous but comes after treatment decisions that were made earlier. So I mean, you might say the statistics, if we distinguish between randomization and sequential randomization, and I think when you're saying exogenous, you're saying there are decisions that are exogenous, but they're taking place after earlier decisions that I made. So they have been.
How about conditional exogenous?
Yeah, I don't know.
Or call it conditionally independent, conditionally random, and pick your favorite term. But what I mean by it is just it does not depend on unobserved heterogeneity for the unit at hand. So there's no like self-selection or things like that. All right. So again, the typical settings where this might be used in machine learning, right, or in clinical settings, say, are settings like this, like gameplay or like running adaptive clinical trial where you observe patient mortality or morbidity, or it might be the kind of online profit maximizing settings for pricing or reserve price setting in auctions, or like selection of search engine results or social media feeds and so on, recommender systems. And in all those settings, the key point is that that the reward is unobservable. I mean, sometimes there's complications because the reward might be observed with delay, and then you might care about things like surrogates to get there. But by and large, the point is you're maximizing something that you can directly measure, and you measure exactly the reward for the actions you have chosen, but not for actions you have not chosen. Right? So that's kind of a version of the fundamental problem of causal inference. You get exactly the potential outcome for the chosen action, but not for counterfactual actions. But now that gets more complicated when we start thinking about this type of economic settings or social welfare in the way that economists would define it, where kind of a typical way, say, public finance economists or micro-theorists might write down social welfare is as a weighted sum of utilities. So here the omega i's is in some sense how much I care about increasing the welfare of person I relative to other people, and the ui is how well they're doing. Right, so the welfare weights, they are a normative choice. That's kind of not really an empirical object. It's just something you have to take a stance on. How much do you care about inequality, or how much do you care about helping, say, people with sickness or something like that? But then you have the utility of individual I, and that's kind of has this double role in econ between both determining what people choose, but also determining how we think, or what we think is good for them, right? And it's kind of equating the two. But the point is we don't observe the utility, we observe the choices, right? And so that means when you face the type of setting and you care about maximizing some notion of welfare, you never observe the reward for your chosen action, you just observe behaviors that allow you to make indirect inferences about welfare. And so to go back to my binary choice example, right? And again, for the non-economists, please interrupt me if this doesn't make sense. But the basic idea here is we observe the choice. The choice is 1 if the price is less than the willingness to pay. Right? So if xi, the price, is less than the willingness to pay vi, then the individual is, say, buying the object, and otherwise it's not. And the corresponding utility that they get is the difference between the willingness to pay and what they actually pay. Right? So, and when the price is higher than the willingness to pay, then nothing happens. You get no utility out of the interaction. But if the price is lower than what they are willing to pay, then the difference is their utility gain. Or equivalent variation or compensating variation, there's various names for that. In this case, they're all the same, just for the economists, because there's no income effects. And there's a useful way to rewrite this, which is as follows. We can rewrite this difference here between vi and xi as the integral of the response function. Right, so this takes a second of staring maybe, but here this response function is going to be 1 until x hits the willingness to pay, and then it's 0 afterwards. So it's exactly a difference between vi and xi if vi is bigger than xi. Right, and so another way of saying that is it's integrating the response function or the potential outcomes, And if we average across individuals, we get that the expected utility for a given price is the integral of this demand function, which if you've taken like an intro-econ course, you would often see something like consumer surplus is the area under the demand curve. That's what's kind of being reflected here. Does that make sense? Right.
Is there expectation missing in the second equation? Because that's would be a function of xi.
Sorry, which equation?
Yeah, the second equation.
One here?
Yeah, because the right hand side is
Oh, sorry. This should be a little x here. This shouldn't be xi.
a little x.
Yeah. Okay. Right. So this is the expected utility across people, or the average utility across people, if I set the price to little x. And so this should be the integral from little x to. Thank you. Okay, so why does that matter for like the topic at hand, things like reinforcement learning and bandits? Well, now kind of a slightly more complicated version of the same thing is a type of social welfare function that public finance economists might write down, which is some combination of the tax revenue you get from, say, setting a tax rate xi and the utilities that people experience. And the tax revenue looks just like what we had before in the monopoly pricing case, right? In a setting where say a seller sets prices online to maximize their profits. But then if you're like a tax authority, you don't just care about maximizing your revenue, you also care about the welfare of people. And so we have the second term with some weight lambda here. Don't worry about the details necessarily, but the key point here again is to know the social welfare at a point. It's not sufficient to observe behavior at that point. You need to observe behavior at counterfactual prices or the counterfactual tax rates here. And if we think about that in an adaptive decision-making context, like a multi-armed bandit, that changes how we need to explore, right? As I was talking before about the exploration-exploitation trade-off in multi-armed bandits, but you only ever need to explore kind of actions that are potentially optimal in bandits. That's different here. In order to compare two policies, I need to know the behavior between those policies to get the entire integral here. And so that makes it systematically harder to do the exploration-exploitation trade-off, but it's still feasible, but you need to modify your typical bandit algorithms to address these economic settings. Again, because causal inference is harder here because you don't directly observe the outcome you care about, you only indirectly infer it from counterfactual actions. So this is something we discuss in this paper which came out last fall. Now, so this is a sense in which caring about these economic settings makes causal inference harder, right, if you care about social welfare. But there's another sense in which it can also be a lot easier. And that's where these ideas of mechanism design come in, where actually you can get individual level treatment effects, or individual level counterfactuals. And so here's actually a fairly old idea, so I think it was introduced in 1964, or at least published. Here's a simple mechanism that they describe in that paper. Imagine I'm an experimenter, and again, this binary choice setting, but rather than just assigning a price to you and telling you what the price is, I just write the price down, but keep it secret, right, without telling you. But I commit to it, but it's just written on a piece of paper that I don't show to you. And then I ask you what your willingness to pay is. How much are you willing to pay for the good? And you tell me some number VI. And then after you do that, I'm going to do the following. If the willingness to pay you told me is higher than my price, I'm going to sell it to you at the price that I wrote down. And otherwise nothing happens. Okay? And so now what's in that setting, what's optimal for you to do? Basically the best thing you can do, regardless what you believe about how I write down my price, is to truthfully tell your willingness to pay. Right? You never want to report it lower than what it is, because then there's some chance that I actually wrote down a price between what you tell me and what it actually is, and then you would be losing out some chance of getting the thing that you want. You also never want to tell something higher, because then there's some chance that you get to buy it at a price that's more than you're actually willing to pay, so you don't want to do that either. So what economists call a dominant strategy here is to just truthfully report your willingness to pay. But by doing that, you don't just tell me what your response is to the price I wrote down. I indirectly get your response to any possible price I could have written down. Right? So I get all your counterfactual demand, all your counterfactual response functions. And that's extremely useful if I think about causal inference, and it's useful if I think about this bandit type settings, right? Whether for like the profit maximizing context or the welfare maximizing context, because it basically eliminates the incentive to explore for the experimenter. It allows me to completely separate the experimental design from the decision making here, because I get the full information for everybody regardless, and I can choose prices that are just targeting my objective, whatever it is. Right, so another way of saying that is I've reduced the bandit problem to an online learning setting. Right, where online learning is a setting where the data are given independently of my actions. Right, so for every unit of observation here, I get a lot more observation, a lot more information than just the response to that given price. I get the response to any counterfactual price. So that obviously doesn't apply to all settings of causal inference. You might think this is kind of specific. It is a fairly common economic setting, but it is a setting where kind of we do get individual level counterfactuals if you're willing to assume that people are playing dominant strategies here. All right. Questions about this before I move on? So there's. Oh yeah. So I mean, this is incidentally also something that tech companies, my understanding is, do actually a fair amount of. For instance, when they sell ads online, right? The way like Google and Facebook and these companies make money is by selling ads. How do they sell the ads? They run auctions basically for ad space that are kind of run in an automated way. And these auctions, one feature that they often have is a reserve price. It's a minimum price at which they're willing to kind of sell that space on their website. And that's set exactly using a version of this idea it's called second price auctions with reserve prices or mechanisms like that. But again, those are mechanisms where it's optimal for the bidders for these ads to truthfully reveal their willingness to pay, and then the companies can use that to learn the distribution of willingness to pay, to set profit maximizing reserve prices, extracting all the surplus from their bidders. Right, that's a version of this idea where I separate the learning of causal effects or counterfactuals from using this information at the same time, using a mechanism like the hidden price. And it turns again the bandit problem into an online learning problem, in this case for the profit maximization of Google and Co. All right. So the last thing I wanted to talk about here is how do we elicit externalities. This is going to get a little bit messier. This is something I've started recently working on, so very much work in progress. But the key idea here is to care about settings like in environmental economics or in the regulation of data collection and so on, where there are externalities. And then again, externalities are cases where my behavior impacts your well-being and vice versa. Where to think about settings like congestion pricing, my driving causes pollution and noise and traffic jams for you, and climate change. And so key question there is then how large are these externalities? How could you possibly learn how much you're bothered by my driving? And that's something that my sense is like the literature in environmental economics mostly just asks people or make some assumptions about, but it's based on, say, like the science of how these things impact others. But we might be interested in actually eliciting kind of in the mechanism design sense, eliciting what people say would be willing to pay to avoid being exposed to others' actions. And so that's what this is about. But that again makes kind of the causal inference or inference and preference kind of one level harder, because my choices tell you something about my utility, about my own actions, but they don't tell you anything about my utility about your actions, right? Because your actions are chosen by you, not by me, kind of by construction. And so how could we do that? And so, yeah, just bear with me for a couple of minutes here. It's getting a little messier. Here's a kind of simple model for that kind of generalizes this binary choice setting of before. So here I've replaced the x by t. You will see y in a minute. But the first part here is just like before, right? We have the binary choice yi. Do I drive or not, for instance? I'm exposed to a price or tax rate t, and I have my willingness vi. So that's just like the same as before. But on top of that, now I'm exposed to this externality, right, where the actions of others impact me. Here I have the v bar, it's just the sum of everybody else's choice, how much everybody else in my town is driving, say. And I'm impacted that by a factor bi, how much I'm bothered by the noise and pollution and traffic jams. And then what we got to design to do that is some mechanism, some cost that you have to pay based on your action and based on what you tell me that this tax rate for others should be. And all right, so yeah, I'm not gonna go through all the details here, but the basic idea is I can pick a way of setting this cost where I'm asking you both, what's your actual, do you want to drive or not, say, what's your willingness to pay for that, but I also ask you how much are you impacted negatively by the driving of others. Now, if you don't have to pay a cost for the second thing, you have an incentive to just give me a very high number, because then yeah, you just get everybody else to stop driving, even if you only care a little. And so to make it incentive compatible to tell me truthfully, I have to be smart about what you get to pay by setting a tax rate for others. And turns out one way to do that is using this kind of quadratic scheme. And again, I'm gonna, in the interest of time, I'm gonna skip the details here. But the high level point here is I can design a scheme here where I'm asking you to tell me what you want to do in terms of your own driving, but I also ask you how much you're bothered by other people's driving. If I set this pricing scheme in a smart way, it's again dominant strategy. So it's again makes sense for you no matter what to tell me the truth here, and I can incorporate that in a similar adaptive scheme to say learn optimal rates for congestion pricing or something like that. Sorry if this last part was a little bit in the weeds, but the point is kind of this is kind of yet another dimension of how the causal inference problem can get more complicated here, because it's inference about the impact of your actions on my well-being and the other way around. But we can devise solutions to that to build this kind of welfare maximizing adaptive algorithms. And just to wrap things up, just some shameless self-promotion. We briefly mentioned it, but I have this book which came out last fall, The Means of Prediction, which is more about the social and economic impact of AI and the regulation of AI, which builds on some of the ideas I discussed today, and more broadly kind of thinks about AI as automated decision-making using optimization, where a lot of the existing discussion is about optimization failures, right, in various forms and shapes. But the argument of the book is instead it's about what do we choose to do to optimize here, like in this reinforcement learning embedded settings and so on. And then about who gets to actually choose that, which relates a lot to thinking about the relevant inputs of AI, relates to things like scaling laws, the production function of AI, and then finally makes a case for closing the gap between what we do optimize and what should be optimized from a social perspective, building institutions of democratic control for AI decision making. Happy to talk more about it offline. And other than that, thanks for your attention. And
me?
sure.
As a non-economist, I'm curious why you framed social welfare as a problem of moving away from optimality as opposed to just having like global externalities added, or I don't know if that's the right term, but having a social welfare component added to each individual utility and still looking for an optimal solution.
You mean for the last thing I talked about?
No, the social welfare slides. You said you're no longer looking for you now have to explore suboptimal actions,
Yep.
and I think that's because you just didn't change the definition of utility. But you could also change the definition of utility to include a social welfare term in everybody's individual utility and look for an optimal solution. Not that that would be feasible.
So there's kind of two sets of people acting here, right? There's the people who are being exposed to the tax rates, say, or prices, and then there is, like, say, the social planner or the algorithm who picks the tax rates. The individuals here, by assumption, kind of care about their own welfare here, right? They are going to pick their actions to maximize, say, this utility here. And as a social planner, I care about their utility and my tax revenue.
I guess the question is why the assumption is that the utility is only the individual's utility and not a utility that includes a social welfare component, like a global social.
So that is what the algorithm is trying to maximize, is the global thing, right? But what this point here is about is to say, I don't observe social welfare, me as the algorithm or me as the planner. I observe people's behavior.
Okay.
And I can learn from behavior about the social welfare. And that involves expressions like this one. But because this expression doesn't depend just on the behavior for the chosen policy, it depends on the behavior for counterfactual policies, that makes it kind of a systematically harder learning problem, where basically I have to do experimentation away from the optimum, which kind of slows down the algorithm relative to a standard bandit case.
Susan.
Yeah, I have two comments, and I know you're kind of aware of these, but to sort of, for the broader audience, I guess, going back to, the first one is going back to the original discussion about, like, exogeneity and why, you know, maybe it's not so interesting to study inference in bandits. I guess there's, like, two questions. One is identification, and you were really talking about identification, but, like, there's also estimation, and we would have been, like, done with, you know, a bunch of causal inference in the 1980s if we weren't interested in estimation. And so the estimation problem in contextual bandits and reinforcement learning is quite interesting. And there are several groups. My lab at Stanford, although these days I haven't done as much in the last year or two on this. John Langford's group at Microsoft Research and a few others have really gotten into the estimation details and shown that it does in fact affect the performance of reinforcement learning to bring in the ideas of estimation from the causal inference literature to reinforcement learning. So those of you who haven't, there's a big part of the reinforcement literature, learning literature, who hasn't noticed this, but there's a subset that has, and it's a very interesting place for future research. I think it just lost a little steam because everybody got interested in generative AI. But it's still very interesting from an estimation perspective. And then the second smaller comment is on this, like, I also have done a bunch of these surveys where you try to learn about people's preferences using surveys, but there's like a big gap between that and in actual practice, in the sense that, like, whatever people tell you, even if you've incentivized it, is often still not what they do, and so you still...
You like the PDM type stuff for...
Yeah. Sorry?
You mean like this type of the PDM mechanism type stuff? Or?
Yeah, I mean, just that people's decisions are impulsive, or like when they're, you know, that there's a big lack of external validity from what you get out of these things. I mean, I studied misinformation and people's willingness to share, and so I'm using these methods too, so I'm not criticizing using them. It's just that it's not a panacea, because people's decisions in the real world can differ.
Yeah. I mean, fully agree with everything there. I mean, on the estimation reinforcement learning part, there's a bunch of aspects to that, right? I mean, one is part of like powered alpha, zero AlphaGo, and so on, was like the whole deep reinforcement learning, bringing in the neural networks to actually think about estimating these value functions, because you have like a very high dimensional context space and so on. There's the issue which...
I'm sorry, my point is not that like neural networks can do it, and that's what's interesting. My point is that those people get things wrong when they don't take advantage of what we've done in statistics.
Yeah, and there's been like stuff that you've worked on also, right? Like the surrogates and things like that, or reinforcement learning just more generally. It takes a long time for the actual outcome you care about to be realized, and so you can use various things to learn more quickly along the way, to use intermediate information in some way or other. So I think, yeah, absolutely, there's a lot to be done there that's interesting.
We had this, why don't we go with the hands that were up? I think you two, and there was maybe somebody back over there.
No, I'm retracting the question. Thank you.
I was just following up on Bets's comment. I was just wondering, I mean, I don't know, is there room for a situation where I get utility if I think other people are getting utility?
Absolutely, yeah, I mean, that would be a form of an externality in some sense. Yeah.
I was just wondering what is the role of the covariates here, because in biological systems I don't think of the observed covariates or playing some role, but here I would think the behavioral aspect comes into play than just
And for like this contextual bandit type setting, right, like the role is to do targeted treatment assignment basically, right? Different people say have a different willingness to pay for things here, and the more information you have, the more of that heterogeneity you capture, and the higher the rewards are that you can get out of an algorithm like this. But in principle, it can be anything. In this type of setting, it's assumed to be exogenous, and in like a proper reinforcement learning setting, it might be endogenously involving state of the environment. I don't know if that answers your question, but yeah.
One more, go ahead. Never mind, let's stop. Sorry.
Okay.
Okay, so
Happy to chat offline.
thank you.